My name is Hossein Kabir. I'm a PhD student in Construction Materials Group at the University of Illinois, Urbana-Champaign. And today I'm going to talk about how to predict sorptivity based off surface wettability. So sorptivity is a term for concrete materials. It characterizes concrete by saying how much water it absorbs as a function of time. And I'm trying to include computer vision approach to make it more viable. So what is contact angle? So if I place a single drop on the surface of cement paste, at the ternary phase where we have gas, liquid, and solid, if I draw the tangent line, if I read this angle, it's called contact angle. So if the droplet spreads on the surface, if the angle is less than 90 degrees, we call it hydrophilic, and if the degrees is more than 90 degrees, we call it hydrophobic. And there is another terminology called wettability. It shows how much a droplet wets the surface. So for excellent wetting, the theta value is close to 0. But if the drop, let's say if I coat my concrete sample with hydrophobic agent, the droplet will stay on the surface and we have poor wetting. So how to measure contact angle? So there is a very, very simple device called contact angle goniometer, which measures the contact angle. So we have a light source, we have a camera, we have a mechanical stage, and we have a syringe that dispenses water. And look at the price of this device. I mean, you can buy a very good spectroscopy device with this money. Why is it so expensive? Because the software is licensed. So either you have to develop your own software or you have to use their licensed software. So my goal was to develop an inexpensive goniometer, which is way cheaper, and instead of one camera, we have 2 cameras. So these cameras you see in a dark room are called USB microscopic cameras. These are like $20-30 on Amazon. And this is like a XYZ mechanical stage. It's also $50 on Amazon. So the thing is, with very simple setup, you can capture the behavior of droplet on the surface of your cement sample, and this will be the results. So either the room is dark and the camera has its own light source, is called front lit illumination. In the middle, we have normal lighting condition. So this is like, and this is like the vice versa. So here's the thing. I need to train my model, a deep learning model, to give me the contact angle values, and then I use that contact angle values to predict sorptivity of concrete. So I was so interested to capture the behavior of droplet, but something I initially neglected was the Kolmogorov complexity. So if you look at this image, it has many features. I mean, probably you have seen this image before. If I zoom into one spot, it's like endless features that I can detect. So Kolmogorov complexity is the length of the shortest computer program that produces the object as output. So initially, if you look at this image, the droplet, the grayscale droplet, each pixel has 2 to the power of 8 values, can have any value from 0 to 256. 0 means dark, 255 means bright. And I trained my CNN model based off that. So my input was these images, and the output was the tangent angles. And I got very, very unstable results. So I was like, why am I getting this? So I simplified my image, and I binarized my data. So instead of like 129 kilobyte of image data, now have 3 kilobyte. So now each pixel has a value of either 0 or 1. And if I look at the training of my model, it's now well trained. So if you are working with image, either you should have a lot of a big data set to properly train your data, or you can reduce the complexity of your image by doing that. Another way you can reduce the complexity, like for crack detection or for any other things, you can zoom into the region of interest and you can exclude your background, your useless background, because those background will confuse your models. So something else I noticed was when I dispense a droplet on the surface of concrete, it spreads on the surface. So what happens when droplet spreads on the surface of concrete? So the focal distance of droplet changes. That means the droplet becomes more unfocused. So if I measure the signal to noise ratio, the noise, the SNR decreases from 40 decibel to, from negative 20 to negative 15 decibels, which means that my model, like the boundaries becomes unfocused. So I artificially blurred my image in Python using Gaussian blurring filter. And I was curious to see how the proposed method will perform compared to the existing method. So the existing method, which is based off the goniometer I showed you earlier, the commercial goniometers, fit a polynomial to the boundary of droplet by analyzing the signals. But convolutional neural network becomes unstable at around GB of 25, like somewhere here. So this image is still recognizable by CNN. So this is like a real-time measurements of the data I have. So it converts the data to a binarized image, and then it measures the contact angles. And not only with one view, I can do it with multiple views. Like here, I have view 1, view 2, like 2 cameras are facing one image. So I talked about contact angle, but why is it useful for concrete and cement industry? So in ASTM C1585, we have a test called measuring the water absorption of concrete. And this is my concrete sample. And it says we have to seal all these faces of concrete except the bottom face. And the bottom face is touching water. And with time, so I normalize the mass change, it's called penetration. And I plot it with, as a function of a square root of time. and I get two linear lines. So the first one is called initial sorptivity. The second one is called secondary sorptivity. So initial sorptivity tells me about resistance of concrete to physical sulfate salt attack. And the secondary sorptivity gives me an idea of the resistance of concrete to freeze-thaw attack. But the thing is, this test is very labor intensive. You have to constantly measure the mass change of sample. One may say, well, it's just mass measurement, but think about it, you have to do it for 12 hours frequently, and then for the next few days. So I analyzed different systems, like different paste samples initially. These are like different systems with different water cement ratios and cured for different times, 1 to 7 days curing. And I noticed that the initial contact angle of droplets, if I plot this with the sorptivity for 63 different cement paste samples, we get a nonlinear correlation. So that means if the matrix is dense, it doesn't allow water to get in. So the contact angle will be larger. The other thing it gives me is instead of waiting for 6 hours to get one slope, which is this one, or this one, it gives me an idea of the sorptivity in a matter of seconds. And of course, I noticed that the time which is required for the droplet to be absorbed by the surface, I call it droplet residence time, is also correlated with the sorptivity. So here's the schematic of how, like these are different cementitious surfaces, and each column is one sample, and this is a time scale. So this is 0 seconds to 2 seconds. So if the matrix is too dense, it doesn't allow water ingress. If I dispense the water, it will remain on the surface. But if I place droplet on a very porous sample, then the droplet will immediately vanishes. So this graph somehow confirms that dynamics of droplet can be correlated with the absorption rate of cementitious systems. And also, this is another schematic that shows like how droplet behaves on the surface. So now there is no need to use any expensive goniometers, but we can use our own technique. And it doesn't matter if you use CNN, ANN, random forest. As long as you have a good data, you're able to train your model. And then with this inexpensive goniometer, in a matter of few seconds or few minutes, you're able to predict how much water your system can absorb. So that's my presentation, and these works are, I guess, accessible, and you can find them from these papers. And with that, I'll happy to take any questions. Yes.
Hey, awesome presentation. Thanks for that. Can you comment on how model architecture and regularization played in your predictions, especially as they relate to generalizability?
Sure. So it wasn't a deep CNN again. So it was like 3 to 4 layers of CNN, and then the images were 448 by 448 pixels, this is somehow like if you input square images, it will at least make the training more rapid. And then that was like this number of neurons was like very similar to like, so I had like 4,000 images initially, and if I when I trained that on the normal images, I wasn't able to train them, so I had to like bring it down, and then that was like a very simple model, and then the input was a matrix of numbers. So that's like how CNN works, and the output were like two outputs, like left and right contact angles.
I think it was more targeting, like, was there any sensitivity towards different architectures, and did you regularize the model?
I regularized the model,
Okay.
and also it wasn't highly sensitive to the model. I also used random forest because that's also can be used to train a matrix of numbers. Yeah, so that's it.
Cool.
Thank you. Yes.
I think this was quite impressive, what you found between the contact angle and the sorption. But one problem may be that in reality the surface is different from the layer beneath the surface.
Yes.
Did you test this on cut surfaces or on cast surfaces?
So that's a great question. And so first for concrete, we need to use, like we're now trying to use multi-channel pipettes, and we're trying to detect multiple droplet images at the same time. But for real concrete surfaces where we have carbonation, the surface is more densified because of carbonation. So again, similar to carbonation depth, where we split the sample and spray phenolphthalein, we have to test it on a fresh concrete sample. Or in the lab scale, we can use it like we can put it in like under desiccator or an area which we are not sure if it's like to make sure it's not carbonated. And also, this is like trained on unmodified surface. So if I make this surface, like if I sandblast the surface area of my sample becomes like larger. So it will have more contact with droplets. So it will expedite the spreading of my sample, which I did, and I noticed that they should have like roughly similar roughnesses. Otherwise, it's very difficult to get a good conclusion.
Thank you very much.
Thank you.